Hello everybody and welcome again to the NPTEL online certification course on microelectronics devices to circuits. In our previous lecture schedule we had seen how a common source amplifier works and what do you mean by mid band frequency, what do you mean by lower cutoff frequency, and what do you mean by higher cutoff frequency or upper cutoff frequency. How do you define bandwidth, what is the meaning of gain bandwidth product, and this is one of the figure of merits which we have discussed. We also saw why does the gain falls off at relatively high frequencies and low frequencies and remains stable independent of the applied frequency somewhere in the mid band. Then we saw the mathematics of it, and we saw that if we do have a common source design at low frequencies, the capacitances are open circuited, at high frequencies they are shorted. We are left with two important parts which we did not carry forward during the previous lecture series, and that is what we have actually seen is the Miller capacitances. We have already discussed with them together, but I will just refurbish your memories here. So, let us suppose I have I want to just refurbish the whole thing. So, let us have a 2 port network, this is port 1, this is port 2, and I have V1 as the voltage source at port 1, and I say at port 2 the voltage V2 is equals to K times V1, which means that the voltage at V2 is a function of V1, right. So, there is a sort of a feedback loop between nodes 2 and 1, right. Now, this can be replicated as, that is what I was saying, it can be replicated as like this, right, where this is basically Z1, this is V1 once again, and this is Z2, and this is again replicated where this is V2 and where obviously equals to KV1, where we can write down Z1 to be equals to Z over 1 minus K and Z2 equals to Z over 1 minus 1 by K. A formal proof at this stage is beyond the scope of this course, but this is how it works out, which means that if I ground those two capacitances I get it. Now, in my previous discussion we saw that when we are doing high frequency response we saw that C in will be equals to CGS for a common source amplifier, CGS plus CGD multiplied by 1 plus GM times RL prime, right. This is the high frequency response which we got, where RL prime is nothing but the resistance RL parallel to RD parallel to RO, right. So, this is basically your RL prime, right, and this quantity is referred to as a Miller multiplier, which means that the gate to drain capacitance which was initially a low value in reality gets multiplied with 1 plus GM RL prime and effectively gives you a larger value, which means the reason being GM is typically large, right, RL is also large. So, this quantity is a relatively large quantity. So, that means even if the gate to drain capacitance is small, its effect on the output is relatively large, right. That is what I wanted to give you an idea about or place an idea about. And the reason being that which means that therefore, when two ports are connected by an impedance just as gate and drain are connected through a gate impedance, then we can refurbish or re-clarify it and we get this structure into consideration, right, and this is what we get as the output capacitances. Now, let me come to we have also seen that there was a source degeneration resistance concept which we have seen, right, and we saw that if that is true, which means that if I have got a common gate, that means I have got a this and I have capacitance here and I am driven by V sig, right, and I also have a resistance here, right, this is your Rg and you have Rd here, right, and then this is a cap here and then you have RL here, right, and this is your V out and this is your VDD, let me say grounding it. Now, under this criteria this is also referred to as source resistance Rs, right, and what happens is that the effective resistance seen from the source side is basically 1 by GM plus Rs, fine. So, if you look from the source side, which is the source end of this MOS device, the effective resistance seen by the device is 1 by Gm plus Rs. With this knowledge, let me write down for you R in to be equals to Ri, that is equals to almost equals to Rg, right, because the gate resistance is the largest one and you get this. Therefore, I get Vi input voltage, which input voltage is the voltage at this particular point at point x, will be equals to V sig, right, signal into Rg plus R sig. So, this is R sig, right. So, V I equals to V sig into Rg. So, it is basically a potential divider network which you see. Therefore, I can safely write down Vgs, right, equals to Vi into 1 by Gm upon 1 by Gm plus Rs. Why? Very simple. If you look, Vgs is the gate to source voltage which is applied here, right. Vgs is the gate to source voltage, this one will be nothing but, so not all of Vi will appear as gate to source voltage, a part of it will appear across gate to source voltage depending on this value of 1 by Gm upon 1 by Gm. Why? Because this is the resistance of the device itself and this is the resistance of the device seen from the source side, and therefore, if we divide it, I get this into consideration. This will be approximately equals to Vi upon 1 plus Gm times Rs. So, if you find out Vgs, therefore comes out to be Vi into 1 upon 1 plus Gm times Rs, right, and this is the source resistance which you see, right. Therefore, if I want to find out the drain current ID will be given as Vi upon 1 by Gm plus Rs, and this will be approximately equals to Gm times Vi upon 1 plus Gm times Rs. This is equals to ID, fine. Now, we very well know that VO output voltage will be minus ID times, right, RD parallel RL, where RD and RL are what? Suppose this is RL, this is RD, then we define V0 equals to minus ID, the phase change is there, therefore, there is a negative sign. So, if I can safely write down this to be as minus Gm times RD parallel to RL, right, divided by 1 plus Gm times Rs into Vi. This so this is what we are doing, we are placing it here and plugging it here, and therefore, V0 by Vi, which is nothing but the AV gain, is equals to minus Gm times Rd upon 1 plus Gm times Rs, where Rd is the drain resistance. If you actually see the overall resistance, assuming that your RL is much larger as compared to Rd, and this is true also, right. So, I get overall gain AV to be equals to minus Gm Rd upon 1 plus Gm Rs. So, if you look very carefully, or if you want to have a look into the careful consideration, you will see that your presence of Rs actually lowers the gain, right, and it makes the gain low, because as you increase the value of Rs, the denominator increases and as a result it becomes low, and as a result what happens is that your gain starts to fall down. But the interesting part is that, as I discussed with you earlier also, that this presence of Rs actually helps you to do a negative feedback and stabilizes it. So, though your gain falls down, your bandwidth increases, because the gain bandwidth product is always fixed for a system, right. So, that is the advantage of having this resistances available to you. Now, if you look at this equation here, so let me just write down in a clearer fashion that AV equals to minus Gm times Rd upon 1 plus Gm times Rs. Now, obviously Gm times Rs is much larger as compared to 1, therefore, I can safely write down AV to be equals to minus Gm times Rd divided by Gm times Rs, right. So, this Gm cancels out and you are left with minus Rd by Rs equals to gain, right, which means that if you want to find out the gain just by inspection, look at the drain resistance, look at the source resistance, but there is an issue here that you will see in the source resistance extra term 1 by Gm will also come into picture, fine, because when you see from the source side, that is the extra Gm which has already come already. If you remember correctly, it has already come. So, you need not put this one, but typically RD by RS will be the value of AV which you get in such a scenario, right. So, this is what we get from our previous discussion and our knowledge as far as this design is concerned. We have also understood the basic concept. Let me come to the next one, which is basically a common gate design, right. Common gate is grounded, and therefore, I will do common gate design, not very seldom used it is not basically seldom used, it is also known as a source follower design, which means that it's a follower, which means that its gain is almost equals to 1. So, Rn equals to 1 by Gn, as I discussed with you, Vi equals to V sig 1 plus Gm times R sig, right, and therefore, I get Rin equals to Rg approximately, and therefore, I get Vi equals to V sig into Rg upon Rg plus R sig, since, and therefore, Vi will be approximately equals to V sig, because Rg and R sig, because R sig is very small as compared to Rg. So, I get V0 to be equals to Vi into RL parallel to R0, right, into RL parallel to R0, right, plus 1 by Gm, fine, and therefore, I will get open loop gain AV0. So, this Vi will come in the denominator. Since RL is much larger as compared to R0, I can really write down this to be as R0 upon R0 plus 1 by Gm, right. Since in reality R0 is much larger as compared to 1 by Gm, we can write down AV to be approximately equals to 1, because this will be very small, this cancels out, I get 1, right. So, in a common gate configuration, the gain is always equals to 1, and therefore, it is also referred to as a source follower, and generally they are used as buffers, right, they are used buffer. So, with this discussion we have finished with the 3 configurations available to us, and these key configurations are common source, right, you have got common drain, and you also have the third type, which is common gate. So, there are 3 configuration. The most seldom used is this one because of its high gain. This is source follower, which is used for impedance matching purposes, right. With this we have finished the basic concept of single stage amplifier and how to design a single stage amplifier from MOS devices. We now come to a new device, which is the topic of this module, and that is known as JFET, or junction field effect transistor. We will look into its structure and its operation in this module, and in the subsequent modules we will discuss other parts of this structure. Okay. Let me come to what will be the outline of the talk. The outline will be looking at the JFET, or a junction field effect transistor. We will be looking at its structure, how it looks like, then how does it operate when you apply a small drain to source voltage, and when you apply VGS equals to 0, how does it operate. We look at the IV characteristics and then recapitulate our ideas about JFET, right. So, this is what we will be doing here. So, again as a MOS device, this is also a voltage controlled device, which means that this is basically again a voltage controlled current source. So, you will be applying a voltage and the current will be changing in the output side. So, the current in the JFET is therefore through a semiconductor region known as channel, and with the ohmic contacts at each end. Ohmic contacts means which follow IV current versus voltage linear graph. So, this is basically this is the Ohm's law, right, because so I versus V. So, any contact in which I versus V is a linear graph is basically my ohmic contact. What we will be looking into is how it operates, and that operation will be explained to you in subsequent slides. But the basic transistor action is the modulation of the channel, right, by electric field perpendicular to the channel. So, which means that is something like this. So, if I have a channel in suppose the water is flowing through the channel, right, then what I do is I close the channel from outside by pressing it from both the sides. The channel is getting narrower and narrower. Then what will happen? The volume of water will reduce, right, and as a result, so I can increase the volume of water by opening up the channel, or decrease it by closing the channel. Conceptually the same thing exactly happens in the junction field effect transistor, and let us see how it works out, what the structure looks like. So, if you look at this, on the left hand side is the schematic of a JFET, on the right hand side which you see here is the actual diagram cross section of a JFET. So, if you look very closely, I have this ohmic contact here, I have a drain region, I have a source region exactly like a MOS device. This is ohmic contact. So, it is basically a metal contact, metal semiconductor contact here. I have a gate region also an ohmic contact. So, I have 1 ohmic, 2 ohmic, 3 ohmic and 4 ohmic contacts. Then I have a P region, this is basically P type, this is P type, and this whole substrate is basically your N type, right. This whole substrate is basically your N type. Now, if you look very closely from your previous discussion, and these two gates are this gate and this gate are shorted with respect to each other, which means that if I give a voltage X here, the same voltage appears here as well as here, right. So, it is known as a shorted gate, or the two gates are shorted with respect to each other. So, the same voltage is applied to both the gates. Under such a criteria, we will see how it works out, or how it works in a general sense. So, before we move, so this is the structure which you see, as I discussed with you, the doping concentration here is pretty large. This is also doping concentration is pretty large, and the drain and source you have metal contact here. Now, as I discussed with you, even without application of any external source or external bias, there will be obviously a depletion region which will be here, right. There will be always obviously a depletion region which will be here, right. And this depletion region thickness will depend upon the relative doping concentrations of the P side and N side. But the interesting point will be the depletion region will be equally thick here, here as well as here, right. I hope you agree with the statement that the depletion, since I am not giving any bias anywhere, all of them look equally reverse biased or forward biased, and therefore, the depletion region will be formed equally in all the directions, right, because the doping concentration is same across all the directions. Now, let us see how it works out. Let me see that you did not you first of all, now let us suppose we explain in this manner that I apply on the gate side, this is the gate voltage I am applying, a positive bias, means I am forward biasing the gate with respect to the source, and applying a positive bias here and a negative bias here, right. Let us see how it works out. Let us suppose this is like let me see how you will understand. Let me put VG, let me have a VDS equals to 0, right. Also my VGS equals to 0, which is exactly this graph which you see, or this profile which you see. Now, what I do is I keep my VDS equals to 0, right, and I go on increasing the value of VGS, right, and how do I increase it? I make it more and more negative. So, -1, -2, -3 and so on and so forth. So, once I put to the positive sign a negative voltage, obviously this will reverse bias with respect to an N channel, right, and as a result what will happen is that this will grow, and this will grow what equally in all directions. Have you got the point, right. So, when VGS equals to 0, your channel was fully open, you go on increasing the value of VGS, keep your VDS constant at this stage, go on increasing the value of VGS in a negative fashion for an N channel. If you have P plus as your source and drain and N as your channel, then go on giving more and more negative value to the gate, and you will see that the depletion region and both edges will start growing together, and a time will come when they will approximately touch with each other, though that is a debatable issue, but they will touch with each other, and therefore the channel will be lost, and therefore even now if you apply a drain voltage, nothing will happen, because because those areas are devoid of any free charge carriers, right. So, this is what I wanted to say, that by simply application of a negative bias on the gate side, I was able to control the width of my channel, and therefore the net flow of charge carriers from source to drain. Now, with this idea or with this basic concept, let me therefore explain to you this graph here which is given at this point. Now, let me do one thing. Since you have understood how a channel will be closed, let me do one thing. Now, what I do is I make my VGS equals to 0, and then go on increasing the value of VDS, which I am doing it here. So, you will be obviously certain that when VDS equals to 0, right, your ID will be also equals to 0, because if there is no potential, there is no chance of any electric field, and therefore when there is no electrons will be moving from source to drain, and as a result source is grounded, and as a result there will be no current. But as you go on increasing the value of VDS in a very small domain, this VDS is relatively very small, say 0.2 volt or 0.3 volts, right. The electrons will be moving and it will move fast from this end to this end, and a current will be formed. But and quite interestingly, and therefore you just compare it with flow of water. Water is flowing, the tap is there, I have opened the tap fully, or I open the tap, and then what I do, I start closing it. But when I am closing it very slowly at the starting. So you will not feel the difference in the water flow as such, and therefore it will be almost a linear increase in the current, because you go on increasing the value of VDS, more and more electron will be flowing, and therefore you will get a larger amount of current. But understand one important point, that, and this is quite interesting, that when you make it VDS larger and larger, right, you see, say I will give you an example to give you an idea about it. So let us suppose this is your JFET, right, and this is your P plus region, this is your P plus region, and then what you do is you apply a bias, and you had a this and this. So assuming it to be equal, now you apply a VDS here, and you go on and make it more and more positive as you get. So if you apply 1 volt here, it means that it is 0, so it is 0, 0.1, 0.2, 0.3, 0.9, and then 1. If it is 2, it is 0.2 here, 3, 4, 5, and then it will come to 2 volts here, which means that as you go on increasing the value of VDS, this side will become more and more positive as compared to this side, means all the channels will become more positive, but this side will be more positive. So here it will be 2 volt, here will be, so if you look at very concentrated at this point, when you apply VDS equals to 1 volt, this will be my 0.7, when you apply 2 volts, this exactly the same point will be 0.9 maybe, or 1.2 maybe, right. But understand, this is an N channel MOSFET, sorry, this is an N channel JFET. So with this N channel, and you are applying a positive bias at the N side, you are effectively reverse biasing the P plus N region, and therefore the depletion region on this side will be larger, right. I will just show you what I was trying to say. You see, this side depletion region is thicker as compared to this side, because what this will see is just, it will see 0.5 volts, whereas this will see maybe 1.2 volts if you apply VDS equals to 2 volts. So this side it becomes more and more thicker, and therefore your channel starts to get shallower and shallower, it goes on becoming thinner and thinner. As a result, now what happens is that the channel resistance starts to rise. Obviously, if you are closing something, the resistance offered by the channel will become more and more, and therefore the current which was flowing linearly straight line starts to show a dip here. Why? Because if you remember, resistance is equals to del VDS del ID. So when I was in the linear region, resistance was constant. Somewhere here, for the same change in the value, so somewhere here for the same change in the VDS, there is a smaller change in IDS, therefore this is small, and therefore R is large. So more the slope is, less will be the resistance offered. So you see, so here is heavy resistance, here is almost 0, very small resistance, and here is infinitely large resistance available to you, fine. So when you take VGS equals to 0, this is still the condition when VGS equals to 0, right, and I get this current into profiling. I hope I have made myself clear that this is basically with VGS equals to 0, I increase the value of VDS and I get this into consideration. Now what I do is, therefore I define a term known as VDS sat, or saturation drain to source voltage, saturation drain to source voltage, at which the current becomes independent of VDS. It is almost a straight line, and the resistance offered is infinitely large. This is the schematic of an N channel JFET, and if you look, it is pointing, gate is pointing inwards, and similarly gate is pointing outwards in a P channel JFET, and the direction of current is already shown to you, right, and this is what JFET looks like. As I discussed with you, therefore current versus voltage characteristics of a JFET, if you want to look, it looks ID versus VGS, and it goes like this. And as you can see, now you see, as you make VGS more and more negative, for the same amount of VDS the current starts to fall down, right, and the reason being what the reason being that now when your VGS is more negative, it is helping you to form the depletion layer more and more. So, when VGS equals to 0, this was forming at, say, when VGS equals to 0, then it was the depletion region, or the depletion region was touching each other as, say, VDS equals to 1.2 volts, clear. But now what is happening is that, let us suppose my VGS equals to minus 1 volt, then my VDS at which the pinch off will occur will be just 0.9 volts maybe. So, at a lower drain voltage, I am able to achieve a higher current or almost the same current. So, that is what I wanted to tell you here, show you here. In the saturation region, as the gate to source voltage increases, becomes more and more negative, the current starts to drop down, or current starts to fall, right, and we define a voltage pinch off, that gate voltage at which the current goes to 0 is defined as my pinch off voltage, exactly the same definition which we saw for a MOSFET threshold voltage, right. And this is the equation for the drain current for case of a JFET. IDSS is the value of the current when VGS equals to 0. So, this is your IDSS, right, for VGS equals to 0, and 1 minus VGS by VP, where VP is the value which you see, right. So, I have given you the discussion for an N channel JFET, you please try to extend it to a P channel JFET as well, right, and the answer remains the same as such occurring to you. As I discussed with you, in an N channel JFET, therefore, the saturation region occurs when VDS is greater than VDS sat, exactly the same principle for a MOSFET. So, I am going a bit fast in this case because we already dealt with MOSFET in a detailed manner. Conceptually, mathematically same as MOS device, but cross sectional wise slightly difference in its operational value. For P channel, this is what we say, that VSD is greater than VSD sat. Now, therefore, the current capability of JFET can be increased by increasing the value of IDSS, which is the function of transistor width. I hope you understand. More is the width, more number of electrons will be there, and therefore, even with VGS equals to 0, there will be substantially larger amount of current which will be there, and as a result you will get a much larger profile in this case. As I discussed with you, for an N channel, therefore, VDS sat should be equals to VGS minus VG, which means that for a device N JFET, right, to be in saturation, VDS sat should be greater than equal to VGS minus VP. Please keep this in mind, where VG is the gate to source voltage and VP is the pinch off voltage. So, let me recapitulate to you what we did in this small module of JFET, because we will not be using it too often, because now JFETs are not too much used across the board. So, I should give you an idea about how its working principle and how does it look like, right. If time permits, we will return back to this later on and explain to you some circuit applications, but primarily it is a voltage control device. Its input impedance is relatively very high, because on the gate side, as I discussed with you, you have a depletion region working in the depletion region, and therefore, your forward bias characteristics are typically very low, and reverse bias characteristics ID will be approximately equals to 0, and therefore, impedance offered is relatively very high. The current capability of JFET can be increased by increasing the value of W, right, and typically the current flow is restricted by two important points, VGS and VDS. So, for an N channel JFET, if you increase the value of VGS more negative, I will get smaller current for the same amount of VDS, right, and so on and so forth. The maximum current is defined as IDSS and occurs when VGS equals to 0 and VDS is greater than equal to mod of VP, which is primarily for an N channel JFET, right. So, this gives you a brief idea about my working principle for the JFET and basic structural parameter of a JFET, right. Two important parameters, IDSS, the maximum current flow through a device in an N channel JFET when VGS equals to 0, and VP, the pinch off voltage, the value of that drain to source that gate to source voltage at which the current is exactly equals to 0, right. And for the device to be in saturation, VDS sat should be greater than equals to VGS minus VP, right. With these, let me close the module here, and thank you for your patient hearing. Thank you.